Welcome, everyone. Today, we are looking at a single exam question that single-handedly took down over half the state in last year's VCE chemistry paper. We are diving into the 2025 quinine question, where a staggering 60% of students scored a 0 on competitive inhibition, and only 7% managed full marks on a basic calibration curve explanation. This wasn't because the chemistry was impossible. It was because students lacked a systematic way to link molecular structure to analytical data. Today, we change that. We are going to decode the exact logic ladders the VCAA examiners look for so you can easily climb your way to a perfect 13 out of 13. Let's get started. Traditionally, the quinine tree has been used to treat many illnesses, including malaria, due to the range of different compounds contained in its bark. One of the useful medicinal compounds in its bark is quinine, which is used to make tonic water. Tonic water sold today has a much lower concentration of quinine than in the past. High-performance liquid chromatography, HPLC, is commonly used to detect both the presence and concentration of quinine in tonic water. The HPLC chromatograph of a sample of tonic water is shown below. Explain how retention time can be used to confirm the presence of quinine in the sample of tonic water. 2 marks. It is a typical question about HPLC. The low average mark, 0.7 out of 2, reflects a classic analytical chemistry pitfall. Students often state that quinine has a retention time of 1.415 minutes, as an absolute fact, forgetting that RT is highly dependent on experimental conditions. Here are 2 structured logic paths for this VCE chemistry chromatography question, designed to hit both distinct marking points seamlessly. Option 1, Standard Reference Comparison Path. This approach relies on establishing a baseline with a known reference standard under identical experimental conditions. Premise 1, Controlled conditions. Analyze a pure sample, standard, of quinine using the exact same HPLC instrument, stationary phase, mobile phase, temperature, and flow rate. Premise 2, Characteristic metric. Determine the specific retention time, RT, of this pure quinine standard. Conclusion and match. Compare it to the chromatogram of the tonic water. If a peak appears at that exact same retention time, 1.415 minutes, it confirms the presence of quinine. Option 2, Sample spiking, co-chromatography, path. An elegant, robust method often favored in laboratory practice, because it inherently controls for matrix effects and instrument variation in a single sequence. Premise 1, Baseline run and modification. Obtain the initial chromatogram of the tonic water showing the peak at 1.415 minutes, then add spike, a small amount of pure, authentic quinine into that same sample. Premise 2, Reanalysis. Run the newly spiked tonic water sample through the HPLC instrument under identical operating conditions. Conclusion: a peak enhancement. Observe the peak at 1.415 minutes. If this specific peak increases in height area without any new peaks appearing, it confirms that the original peak corresponds to quinine. Key takeaway for students. An RT value in isolation means nothing. To score full marks, answers must explicitly couple identical experimental conditions with either a matching standard RT or a volumetric peak increase via spiking. Various concentrations of quinine solutions were run through an HPLC instrument to produce the calibration curve shown above. A sample of tonic water is to be tested to determine the concentration of quinine. Explain why solutions of known concentration must be run through the HPLC instrument under controlled conditions. 2 marks. An average mark of 0.4 out of 2 is incredibly low. 68% of students scored 0, which shows that the vast majority of students gave a generic to ensure a fair test response rather than linking the chemistry principles to the specific data on the axes, retention time and peak area. To score full marks here, students must build a logical bridge showing how changing the experimental conditions directly corrupts the quantitative data used to build the calibration curve. Premise 1. Operational impact. Uncontrolled variables, e.g., shifts in temperature, mobile phase composition, or flow rate, will change how components interact with the column, altering their retention times. Premise 2. Measurement impact. If the peak shifts or broadens unevenly, the integration measurement of the peak area, the y-axis variable, becomes inconsistent and invalid. Conclusion: analytical failure. Without reliable and consistent peak areas for the standard solutions, an inaccurate or invalid calibration curve is generated, preventing accurate determination of the unknown concentration. State why the calibration curve should not be used to test a sample of tonic water that has a mean concentration of 130 mg per liter. This is a classic, highly transferable graph analysis question that tests the fundamental hazard of data extrapolation. The logic ladder. Premise 1. Curve boundaries. The experimental calibration curve only extends from a concentration of 15 mg L to the power of 1 to a maximum standard of 120 mg L to the power of 1. Premise 2. Target data position. The target sample has a mean concentration of 130 mg L to the power of 1, which lies beyond the tested data range. Conclusion: risk of extrapolation. Using the curve requires extrapolation, which is unreliable, as the linear relationship between concentration and peak area may no longer hold true, such as detector saturation. Exemplar answers: 1 mark. VCAA accepted a few variations of this core concept. Any of the following succinct points secures the mark. Option A. Focus on extrapolation. The concentration of 130 mg L to the power of 1 lies outside the calibrated range of the standard solutions, meaning the data would have to be extrapolated inaccurately. Option B. Focus on range limits. The concentration is outside the range of the tested standards, which only go up to 120 mg L to the power of 1. Classroom strategy and common trap. While 75% of students got this right, the remaining 25% usually fell into one of two traps. Vague terminology. Saying the value is too high, or off the graph, without using key analytical terms like extrapolation, or outside the range of the standards. Missing the fix. It is worth reminding students that to actually test this sample correctly in a real lab, they would need to either dilute the tonic water to bring it into the 15 to 120 mg L to the power of 1 range, or prepare higher concentration standards, such as 140 mg L to the power of 1, to extend the calibration curve safely. Using item 19 of the data book, name the functional group with the highest priority when following IUPAC nomenclature. 1 mark. This is a straightforward data book lookup question, yet it still tripped up 43% of students. The breakdown typically occurs because students mistake the name of the functional group for its corresponding organic molecule family, or they simply misread the priority table order. Premise 1. Identify the CERLD groups. Identify the 3 circled functional groups in the quinine molecule. Carbon-carbon double bond, alkene. Tertiary amine group, amine. Hydroxyl group, alcohol. Premise 2. Check data book priority. Consult Item 19 of the VCE Chemistry Data Book, IUPAC Nomenclature Priority for Functional Groups. Ranking from highest to lowest priority. Hydroxyl alcohol, OH. Amine, NH or similar. Alkene, C equals C. Conclusion, highest priority group. The hydroxyl group has the highest priority position among the three. Acceptable answers, 1 mark. VCAA accepted either the functional group name or its class name. Hydroxyl or hydroxy. Alcohol. To bypass the table entirely during a time crunch, students only need to remember this single, linear chain. Tier 1, the carbonyl carbons. Who, acids, esters, amides, aldehydes, ketones. Rule, if a double-bonded oxygen is attached to a terminal or internal chain carbon, it automatically claims the suffix of the molecule. Tier 2, single-bonded oxygen. Who, alcohols, hydroxyls. Rule, if there is no carbonyl group, the highly electronegative single-bonded oxygen takes precedence over everything below it. Tier 3, single-bonded nitrogen. Who, amines. Rule, because nitrogen is less electronegative than oxygen, it yields priority to alcohols, but safely defeats pure hydrocarbons. Tier 4, unsaturated hydrocarbons. Who, alkenes. Rule, pure carbon-carbon double bonds hold the baseline priority for functional suffixes, beating out alkynes and alkanes. Halogens and alkyl chains are dropped entirely to permanent prefix status. Malaria is caused by the malaria parasite, which enters red blood cells and feeds on hemoglobin. Experiments have shown that the malaria parasite enzymes involved in this reaction are most effective at a pH of 4.7. The structure of the quinine molecule can vary with pH. Representations of two possible structures are shown below. Identify which structure, Q or R, is most likely to occur at a low pH. Justify your response. 2 marks. This question tests a core biochemical concept that bridges organic chemistry functional groups with acid-base behavior, the protonation of basic amine groups in an acidic environment. With a state average of 1.3 out of 2, students generally performed better here than on the chromatography section, but a substantial 33% still dropped the second mark by failing to explain why the structure changes chemically. The logic ladder. Premise 1, environmental condition. A low pH environment signifies a high concentration of hydrogen ions in the solution. Premise 2, functional group behavior. The nitrogen atoms in the amine quinoline functional groups of quinine possess lone pairs of electrons, acting as Bronsted-Lowry bases. Premise 3, chemical reaction mechanism. In an acidic solution, these basic nitrogen-containing functional groups accept hydrogen ions, undergo protonation, forming positively charged conjugate acids. Conclusion: a selection. Therefore, structure Q is most likely to occur because both nitrogen atoms have accepted protons. Exemplar answer, 2 marks. Structure Q. A low pH environment indicates an abundance of hydrogen ions. Under these acidic conditions, the basic amine nitrogen functional groups in quinine act as Bronsted-Lowry bases and accept hydrogen ions, undergo protonation, resulting in the positively charged structure shown in Q. Quinine has 4 chiral centers. Only one of its isomers is an effective medicine in the treatment of malaria. Referring to the term chiral center in your response, explain why only one isomer of quinine is effective. 3 marks. A 3-mark extended response question, with a state average of just 1.3 means the vast majority of students only secured 1 or 2 marks. The prompt explicitly commands students to refer to the term chiral center, so any response that jumps straight to an enzyme substrate explanation without defining chirality structurally drops the first mark immediately. This is a classic definition, structural consequence, biological mechanism, question sequence. Exemplar answer, 3 marks. A chiral center is a carbon atom that is bonded to 4 different groups. The 4 chiral centers in quinine result in various optical isomers, each with a unique 3-dimensional spatial arrangement. Because enzyme interactions depend on a highly specific lock and key fit, only one of these optical isomers will have the exact complementary 3D shape required to bind to the active site of the target malaria enzyme and be medicinally effective. Quinine acts as a competitive inhibitor in the prevention of malaria. Explain why quinine is more effective as a competitive inhibitor at pH 4.7 than at a higher pH. You may draw a diagram to support your response. 2 marks. An average mark of 0.5 out of 2, with a staggering 60% of the states scoring 0, makes this arguably the ultimate discriminator question on this entire paper. This question represents a masterful synthesis task. To score full marks, students can't just define competitive inhibition. They must actively link the structural analysis from question 5b.2, protonation at low pH, to the intermolecular force dynamics within an enzyme's active site. The logic ladder. Premise 1, core form at pH 4.7. At the optimal pH of 4.7, a low pH environment, quinine primarily exists in its protonated, positively charged form, structure Q. Premise 2, mechanism of inhibition. As a competitive inhibitor, it mimics the substrate by entering and binding directly to the active site of the malaria enzyme, physically blocking the substrate from entering. Conclusion, enhanced binding affinity. The positive charge on the protonated quinine enables it to form exceptionally strong ionic bonds, ion dipole, or salt bridges, with negatively charged groups inside the active site, making it a far more tightly bound, effective inhibitor than the neutral form at higher pH. Exemplar answer, 2 marks. At pH 4.7, quinine exists in its protonated, positively charged form, structure Q. This positive charge allows it to bind more strongly to the enzyme's active site by forming strong ionic interactions with negatively charged groups within the site, effectively blocking the substrate from entering. At a higher pH, quinine is uncharged and cannot form these strong ionic bonds, making it a less effective competitive inhibitor. One, the restating the prompt trap. Many students wrote long paragraphs explaining what a competitive inhibitor is but competes with the substrate for the active site. VCAA explicitly denies marks for simply reciting definitions provided in the stem. The question asks why it is more effective at pH 4.7, not how competitive inhibition works in general. 2. Failure to connect previous sub-questions. VCE chemistry exams are structured like a narrative. Question 5b.2 forced them to realize that low pH means protonation and positive charges. Students failed to carry that positive charge into this question. Once a student realizes the molecule is positively charged, the immediate follow-up thought in an enzyme context must be, what does a charge do? It forms strong electrostatic and ionic bonds to the amino acid residues in the active site. 3. Visual tip for students. The question explicitly notes, you may draw a diagram to support your response. Tell your students that when VCAA gives this permission, it's a massive hint. Drawing a simple block enzyme with a negative sign in the active site, and drawing structure Q with its plus sign locking into it, instantly forces their brain to write down the word bonding, or attraction, securing that elusive second mark. Part 1. Chromatography Pitfalls, Questions 5a.I5a.3. Retention time, RT, is variable. An RT value means nothing in isolation. Students must state that a standard must be run under identical experimental conditions to match peaks, or use sample spiking. Control the conditions. Uncontrolled variables shift RT, which alters and invalidates peak area integration. This destroys the accuracy of the calibration curve. Know the limits. Never extrapolate data. If a sample concentration, 130 mg per liter, exceeds the highest standard 120 mg per liter, it falls outside the valid calibration range. Part 2. Structure and Biochemistry, Questions 5b.I5c.2. Nomenclature shortcut. Bypass the data book by using the mental priority tier. C equals O, carbonyl, CO, alcohol, CN, amine, C equals C, alkene. Low pH equals protonation. In acidic environments, pH 4.7, basic nitrogen atoms act as Bronsted-Lowry bases and accept H+ ions to become positively charged, structure Q. Chirality is 3D. A chiral center is a carbon bonded to 4 different groups. Multiple centers create unique 3D shapes. Only one isomer has the exact complementary shape to fit the enzyme's active site. The state killer, 60% zeros. Why is it a better competitive inhibitor at pH 4.7? The positive charge on protonated quinine forms exceptionally strong ionic bonds with negative groups inside the active site, blocking the substrate far more effectively. If you need my help, please add me on WeChat or WhatsApp and send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.